We're going to continue with partial fractions from last day. Now, one of the things I want to highlight is that we must make sure that the denominator has a degree higher than the numerator. So if it doesn't have a degree higher, if the denominator is lower than the numerator, we need to make sure we divide first before we apply partial fractions. Now, we're going to group partial fraction into three types. So last day we dealt with just the linear factors. So we're going to call that type 1, which I highlighted in green here. So when we have just the linear factor x minus a. We're going to then also look at today partial fractions that have this squared denominator, so x minus a squared term, and we're going to call that type 2. And the third type is when we have the quadratic in the denominator and it's non-factorable. So I'm just going to maybe make a note of this, that when this is non-factorable, we need to check for the discriminant being less than 0. Now this can be done as a type 1 if it has roots. Okay, those get a little bit complicated, so we're going to avoid these for now. But if it's non-factorable, we check that the discriminant is less than 0, and then this type ends up being an arctan type of integral. So we're going to apply arctan to that, and we're going to call this one type 3. Okay, so we're going to do some practice with these type 1 types. So when we have this type 1, we have the linear factors x minus 3, x plus 2. And so we're going to split this up into its partial fractions. So we're going to write this as a over x minus 3 plus b over x plus 2. Okay, and then we're going to set up the equations to allow us to solve for this. So we're going to end up with ax plus 2 plus b x minus 3, and that's going to be equal to our numerator up here, just so that you can see where we're getting this from. That we're going to make that equal to the numerator 6x plus 2. Now there's two strategies that we have to solve this. We can solve this by creating zeros by choosing x's that give us zeros, or we can just set up a system of equations by equating the coefficients. So I'm going to do that. So I'm going to first of all expand this out. Ax plus 2a plus bx minus 3b, and that's going to be equal to 6x plus 2. I'm going to group my coefficient, my like terms, so a plus bx plus 2a minus 3b, and I'm going to group that as my constant, and that gives me 6x plus 2. So I have two variables to solve for, so I need to set up a system of equations. So my system is going to be based on the coefficients on the x term. So a plus b and the 6 in front of the x must be equivalent because they're the coefficient on the x. And similarly, the constant term here must match the constant term on the other side. So there's my system of equations. So I'm going to solve for this. My equation 1 is a plus b equals 6. The second equation, based on the constant, is going to be 2a minus 3b. That's equal to 2. So I'm going to solve for b and make b equal to 6 minus a, and then I'm going to substitute for this b here in the second equation. So I get 2a minus 3 times, instead of b, I'm going to use an equivalent expression of a of 6 minus a, and now I have a system where I can solve for the variable a. So this becomes negative 2 minus 2 minus 3 times negative a. That's going to be positive 3, so I'm going to get 5a, and this becomes negative 18 I'm going to move that to the other side. So I get 5a equals 20. So I get the a coefficient equaling 4. Okay, so that's one result. I can solve for then b. So b is equal to 6 minus, I solve for a as 4, so that gives me the value of b. So b is equal to 2. So I've now solved for a and b. I can now write this as partial fractions, and then I can then integrate these terms. So integrating these terms, I'm going to write these integrals. So I have my a value as 4. So I'm going to write the first integral as 4 over, in this case, is going to be x minus 3 times dx plus, I've solved for b as well, so I'm going to use 2 over x plus 2 times dx. Once I've written these, I can then, these are linear terms in the denominator, so I can then integrate these using the log function. So this becomes 4, so a constant we're going to take outside, log x minus 3 plus 2 log x plus 2. And then don't forget the plus c. And there's my integral. Now, since these are both logs, and I can actually combine these using some log properties. So the x minus 3, that 4 in the front can become power 4 on the inside. When I add logs, it's going to be multiplication. So I'm going to end up multiplying by the x plus 2. And that power on the outside can come on the inside as squared. And then this represents a combined log form of that same integral.